Okay, once again, this is the operation session. Our first section of the operation session is a panel on SDN Exchanges. We've asked people who have some experience with operating test beds that span multiple administrative regions and have been either experimenting with SDN or planning to experiment with SDN, and also support experimenters to come and tell us about the things that they've experienced and recommendations for how we might want to go forward this with GENI. So we're missing one person on the panel right now, who is Russ Clark, who is, of course, coordinating the whole conference. So if you see someone run in partway through, that'll be what's happening there. But we're going to go ahead and get started. And the first presenter is Joe Mambretti, who was an important part of the SDX demo that you saw in the plenary today. So, Joe?
Paging Russ. As you said, he is a busy man. This is a real computer. That one is. Neither of those are correct.
Yeah, we don't have VGA. We only have HDMI.
I don't have an HDMI.
Okay, I can put it on here. And why don't I do that, and we'll have Luke start.
That's a good idea.
Okay, good. Sorry, we're changing the agenda so that I can put Joe's presentation on my machine. So Luke Fowler from the GT-RNOC in Indiana University, and also the GENI Meta Operations Center, operate lots of exchanges between lots of administrative domains, and has also been involved in GENI since the early days. So we'll start with Luke while I quickly fix Joe.
All right, thanks, Heidi. As Heidi mentioned, I'm Luke Fowler. I'm here to talk about some work we've been partnering with on Internet 2 to deploy and operate their SDN networks, which you may think of as like a distributed SDN exchange. And so there's a couple different networks I'm going to talk about today that we've built with Internet 2 over the last couple years. The first one of those called NDDI, and the second one called AL2S. So the NDDI network is sort of where we got our feet wet with production OpenFlow networks. And so this was a 10 gig interconnected network with 6 NEC switches that were deployed around the United States. Still there today, actually, but this was the first SDN network that we deployed with Internet 2. That actually ended up proving out some of these technologies. We thought that it worked pretty well, and the SDN was ready to at least serve some basic production use cases. And so we went and deployed this network that we call AL2S, or the Advanced Layer 2 service. This is a BTOP funded network that interconnects about 30 nodes at 100 gigabit between them. So some of you in this room may be AL2S users, and I think everybody that is an AL2S user is probably aware that AL2S is a 100% OpenFlow network. So all the forwarding on AL2S is SDN using OpenFlow 1.0. We're doing a couple different things with that network. We're running an application that provides a dynamic circuit service called OESS. And then we're also looking to support additional applications on the network through a virtualization layer that I'll talk about a little bit in a couple slides here. So the idea here is, large, nationwide, 100 gig SDN network, production applications, as well as experimentation on the same platform. And so, we sort of convinced ourselves that, yes, this is actually something that SDN is mature to the point that we can build with some caveats. So I want to talk a little bit about our experience having built that. So this is what the network looks like today. If you saw Eric Boyd's talk this morning, he had the same diagram. Again, we have about 30 nodes with a variety of regional networks and peer networks connecting to this infrastructure. From a conceptual diagram, this is sort of the high-level architecture of how these things fit together on AL2S, how SDN control and the hardware substrate fits together. So on the bottom, we have a set of OpenFlow switches that implement the OpenFlow 1.0 protocol. On top of that, we have a box that I haven't talked about yet called FlowSpace Firewall. FlowSpace Firewall is what we're using to provide virtualization on the network. So if you're familiar with FlowVisor, it's somewhat similar to FlowVisor. It's simpler in some dimensions. It slices on VLAN tag instead of a wide range of flow spaces. And it was designed to be a production-ready, scalable tool that could scale up to hundreds of slices if you just have to worry about slicing on VLAN ID. So that, like FlowVisor, provides an OpenFlow interface both sort of southbound towards the switch and northbound towards the application. And we can run a variety of applications on top of that then. And so we see the big blue box over here is the OESS application that I talked about. But of course, other applications can also run on this same infrastructure. So this is sort of AL2S as of a few months from now. We actually don't have FlowSpace Firewall in production yet, but that's something that, as Eric mentioned in his talk this morning, we're sort of in the final stages of planning on. We have a 1.0 release of this FlowSpace Firewall out. We've done some demos and some stress testing on the NDDI network, and we're preparing to deploy it on AL2S. So the software that I was talking about that we're running on our SDN network today is the primary application is this dynamic circuit service. So this is a well-known application in this community, user-controlled circuit provisioning of layer 2 virtual circuits. The difference here from a lot of the other packages is we're doing this all in OpenFlow. That provides a few advantages. One, it's really quick. You can provision a circuit in under a second. You can use OpenFlow messages to react to failures. So we do things like listen for port down messages and use that to initiate failover to backup paths. And of course, you can do something like that in a traditional failure mechanism. So you have a VLAN with spanning tree. You're going to have a port down. Spanning tree is going to recalculate the path, and you'll have a new path. One of the interesting things we ran into that we weren't anticipating when we first wrote this application was there are actually other types of failures that we can discover out of band and react to since we have an SDN here. So for example, we have a performance assurance system which is constantly doing active measurements of the network. We also have some messages that we can send in band to the OpenFlow network through things like packet in, packet out channels. So you may be able to actually do things on an SDN like verify forwarding for a user path and react to that event, even if there's some sort of soft failure that doesn't cause a link down, but you still are having users have their traffic impacted. So we started running into this issue in a couple places in AL2S. In the last couple of weeks, we were able to quickly brainstorm, okay, well, how can we fix this where we're not getting a port down, we're having some soft failures. We really want to be able to allow users to switch to a backup path in this case. One of the really neat things about having this be an SDN substrate that we have a really low level of control on, we realized, okay, we have some metrics that we can determine that do a better job of telling whether the user is actually getting traffic from A to B than is the interface up or down. In about 3 days of development time, we were able to take those metrics, push some changes into OESS saying, if you detect a failure, not because of link down, but because of this other external metric, do the same thing you would do as if there was a link down and switch the path. So that's just sort of an example of something that I think is really powerful with SDN is you have a lot more fine-grained control over the behavior of your network in ways that when you run across something unexpected, you might be able to code around it instead of having to go to your vendor and come up with a solution which likely will have a longer lead time. So that's OESS, what it does, and a little story about how SDN has been useful as we brought this up and have gone through some growing pains. So it is a highly available architecture that we've deployed here. So we have multiple controllers. We have deployed a set of controllers in Chicago that's co-located in the POP with the AL2S equipment there. We have a second set of controllers in Bloomington. All these controllers share state with each other, so we're using CoroSync and related components to build this cluster. It operates such that if any of these nodes failed, the cluster would swap to a backup node and user services would continue uninterrupted. So the typical mode that AL2S runs in today is that it uses a nonstop forwarding mode where if it is disconnected from the controller. User circuits are still transiting traffic, but it can't react to events. So if we had a link go down on the network, even though the users would still have their traffic go across the network in the absence of the controller, as soon as that link fails, if their path was on that link, then their path is obviously affected. If we aren't connected to the controller can't react to that and switch them to a backup path. So that's why we spent quite a bit of time thinking, okay, how can we make sure the controllers are as available as possible? So in the current model that we have today, only one controller is actually connected to a switch at a time. They share a virtual IP. There are a variety of different models here that you might be able to use. Some OpenFlow switches, for example, allow you to connect to multiple controllers and have a variety of semantics there about, are they both masters or is there a master-slave relationship or what? But something important to think about if you're developing a production SDN is what's your controller high availability strategy? What happens if your controller goes away? So what else have we learned? We did a pretty rapid development cycle. It was about 9 months from genesis of this idea to actually having production code and production networking equipment in the field on the NDDI network. And then about 10 months after that, we deployed the AL2S network and started getting a lot of uptick in use on the service. There's a few things to watch out for here that are becoming less of a worry over time. When we started OpenFlow, the controller stack, the vendors' implementations on the switch side were largely untested. We were, building brand new code here with brand new vendor code and sort of trying to make that all work together. I'd say over the last, year and a half, 2 years, that's gotten a lot better, and we're getting, less things that break out the door, if you will. But testing is still really important. So, you sort of become the system integrator if you've got this network equipment with this OpenFlow interface and you're an application, and you're trying to glue them together to create a service. You're the one that's going to have to make sure that works. And not only does it work today, but if you upgrade, code on your switch, is it still going to work? If you make a change to your SDN control app, how's that going to interact with the SDN implementation on your switch? So we've invested quite a bit of time in automated testing. And so this diagram shows some of the test lab that we have in Bloomington that allows us to do automated testing through a system called Jenkins. It's a continuous integration system that a lot of different projects use. We actually use this to control our SDN test harness. So we've got a little MIM switchable switch, Glimmerglass, that interconnects all of our test endpoints and our test nodes. The Jenkins test suite can control that, and so every time we have a new version of vendor code, every time we make a change to the OESS software, to the flow space firewall software, we run it through this automated test suite where everything sort of tests together as a system. We've run into instances where we found something that wasn't necessarily a bug in the vendor implementation, not necessarily a bug in our OESS implementation, but you put them together and you have some weird interaction and you don't get what you expect. And so, one of the things that I'd recommend to anybody doing this again is to spend a lot of time thinking about how you're going to test not only your individual components, but how you're going to test your components as a system and make sure that everything behaves as you expect. A couple different types of testing we do. We do use OF tests for sort of a general baseline performance. So, what is this device in comparison to the OpenFlow spec broadly? We also look for some what we call implementation behaviors not mandated in the spec. So, how fast can it process a flow mod? So, if your application needs to send a couple hundred flow mods a second in some cases, can your switch support that or not? How big are the flow tables? What happens when the flow tables fill up? Are there different flow table sizes depending on what types of match and actions you use? And then we do some burn-in testing as well. So we'll run all these tests in rapid succession, maybe over a weekend, make sure that everything that was working well twice works well 1,000 times. So what have we seen in this testing? I mentioned flow mod processing speed as a concern. We saw in the early implementations that we were working with, we saw some pretty severe limits in this respect, but it's been improving a lot over time. Something that we've been working pretty closely with the vendors that support AL2S on and have seen a lot of change there. I think that every vendor we worked with had an incomplete implementation of the OpenFlow spec. There were certain matches or certain actions they just couldn't support, and that's something you need to know going into your purchasing decisions and obviously into operating the network. You should know that just because the vendor says they support OpenFlow or some other SDN technology, this stuff's all pretty new, so it may not be quite full support from a spec standpoint. And then the other thing that we noticed was that a lot of the stuff is really new, and so even if the vendor thinks that they're complying to a spec, their definition of compliance may be a little bit different than vendor B's, and so you may have inconsistency even if both of them are actually following the letter of the spec. And again, the way you find this out is testing. So we ran into a variety of things like this, but one of the things that Matt Zakauskas pointed out to me earlier today, and is definitely true, is that most of the things we found on these networks are just your sort of boring traditional problems. An optic fails, there's a backhoe that cuts something, there's a line card failure. So while we have seen some SDN-specific issues as we brought these platforms up, the majority of it is still sort of the day-to-day running a network. Things break, you got to fix it type of thing. I think I'll skip these 2 slides. If you'd like to talk to me about controller placement, we did spend quite a bit of time thinking about where in the network to place the controllers and how that would affect things like failover time. And we ended up right now with a central controller in Chicago with a plan that if we needed to reduce failover time for circuit failovers to less than about 150 milliseconds or so it takes a day, we could do some distributed control and approach something like 50 millisecond type MPLS fast reroute. Okay, what other lessons have we learned? I talked about central versus distributed control. Your application, if it's reactive, you may need to think a lot harder about this than OESS. Since OESS is mostly a proactive application, we're actually not in terrible shape if there are small windows where we don't have connectivity to the controller. Some applications, everything might just grind to a halt. So think about that when you're designing your SDN network and your controller placement strategy. I think I've gone over most of the things on this slide. One of the things that we ran into, I haven't talked about yet, is all of this stuff is changing really fast. So we're getting new code from vendors all the time. We're making changes to our software all the time. And so you may want to think about just not being able to run one set of tests, but what would it look like if you're going to have to run multiple sets of these tests concurrently? What's your test infrastructure look like there? And then another thing to think about, if you have multiple vendors and they don't have the same feature set, what's your strategy of dealing with that? Do you have portions of the network that can support features A and B? Do you have a lowest common denominator strategy where you support the things that the vendors as a union support or something else? So something that we've had to wrestle with a bit on AL2S. So I think those are sort of the highlights of some of the things we've learned operating the network. As we look at what's next, the big next step for us is enabling production virtualization. So Eric talked in his session in the plenary this morning about flow space firewall and deploying that as a production service to allow VLAN flow space slicing on AL2S. And we're going to have a lot of the same concerns that we had when we were developing and deploying OESS as we're developing and deploying other applications behind flow space firewall. We think we've done a pretty good job of isolating the resource set and making it so that one controller can't step on the resources of another. But we know that given the some of the specifics of the OpenFlow protocol, that can't be 100% foolproof. So we're going to have to go through the same type of testing scenarios, same sort of thinking about redundancy strategies, testing interactions with vendor code and experimenter code, when we put flow-based firewall in production and we get more applications running on this network. So, it's a big step. It's exciting. It's a little bit scary, but we think we're in a good position here. So, in summary, it's been a, very fast and fun 18 months or 2 years getting this thing up and going. I think it's working pretty well right now. We'll see what happens when we go to the next step. I have confidence that that we're going to have success, but like I say, it's kind of a big step, and we'll see what happens.
I saw a little stub for
Yes.
I'd like to know when that's going to be in production. We're a big believer in NSI and want to see that come along.
Yeah, so I don't think we have a date yet when that's going to be in production. We're planning on using the Oscars NSI module. So we're using Oscars as the interdomain controller behind OESS today. So hopefully it should just plug in fairly easily and not be too much of a burden to get going. So, you know, as soon as that's ready, I think. Well, I don't know. So, you know, the next step is going to be us to get that in the lab to test it, see if it works. And if it works well, then I think we deploy it right away. If there are issues that we run into, then we'll have to deal with those.
Questions from the audience? Now it's working. It's just the magic hand.
So one of the things that you walked through was how you guys, deployed the switches, and then you deployed OESS as your first application, and now you're inserting this new piece, which is the flow space firewall in the middle. Going forward, do you see the control plane software stack sort of expanding upward, things on top of each other? Do you see it more expanding outward, having like a broad layer across flow space firewall, or do you expect it to be sort of like a broad mix?
Right. I think probably both. So we definitely see some people that are going to want to attach directly to flow space firewall and expand this way. We also are seeing increasing number of people that are writing applications against the OESS API. So if somebody wants, circuits across AL2S, my recommendation would, there's a bunch of details here, but my basic recommendation would be use the OESS API, sort of build on top of that. If you want to do something different, then you're probably going to want to plug directly into flow space firewall. As we get more things plugging into flow space firewall, I think some of those things will have their own northbound APIs that people start plugging into, like OESS.
Any other questions? I have one. I have the power of the microphone. So you mentioned that vendors' implementations of OpenFlow are not compatible, or at least not complete in the same ways. And then we also have OpenFlow 1.0 versus 1.3 out in the real world. How do you guys think you're going to deal with either, other domains that are running a different version of OpenFlow, or domains that are implementing some fields that you don't support in Internet 2?
Yeah. That's a good question. So it depends. So we're looking at OpenFlow 1.3 now. As soon as we expect implementations from our vendors this year, we're looking at controllers that we can use to replace OESS. We're looking for 1.3 controllers to use for to implement flow space firewall. So I think we'll be at 1.3 in a fairly short amount of time. So then what happens if we have 1.0 networks adjacent to us? I think you have the same types of issues we have where you have two vendors in a mixed network, is you may end up with lowest common denominator that you just, if you want an end-to-end application that goes across those, you may not be able to do better than what you could do on an OpenFlow 1.0 network if there's an OpenFlow 1.0 network in the middle.
Okay, thanks.
Thanks.
Joe. I already introduced Joe once, so I'm not doing it again for those of you who weren't here before.
Testing. 1, 2, 3. Oh, I get to use Macintosh.
Yeah, I won't tell.
Keep this off video. There you go. Okay, thank you. All right, so I'm going to talk about our experiences with SDXs. I'll first point to this wonderful fabric that GENI has been developing as its own closed system, right? And a complementary fabric complementing InstaGenie is ExaGenie, which is doing some different things. For example, there's projects to interface control planes with 40 gig, 100 gig networks. Might be nice for the GENI world to have a way out to other domains, and that's been under discussion on exactly how to do that, and that's, of course, one of the functions of SDX. So there's a lot of architectural attributes for SDXs. As Chip Elliott mentioned, this doesn't really exist yet. People don't know what it is yet. The architecture isn't firm yet. There's lots of ideas, though. And so basically, it's to enable what isn't today. And what exchanges look like today is something that's very rigid and fixed, especially peering exchanges. You can't do anything with them. If you're an edge process, if you're an edge network, there's not a lot you can do with exchange except peer. So what we want to do is have a fundamentally different kind of exchange where you can actually determine the attributes of that exchange. And you can do this in a peer-wise fashion with colleagues. So domain A wants to have certain functionality, not all, but some subset of functionality, exchanged with regard to resources with domain B. This is how you do it. You do it through this architecture. So we have actually been doing this for some time with a project called the International GENI. The International GENI is a distributed infrastructure which has distributed controllers, distributed domains, multi-domain processes, because people in different countries want to do different things, and that's not even the country as a whole, that's individual groups within the country. So we created, using the glyph fabric, the Global Lambda Integrated Facility, this fabric, which is an OpenFlow worldwide fabric with sites in Europe, North America, South America, Asia, that are interconnected. And our focus, by the way, is layer 1, layer 2, as opposed to layer 3. This is a layer 2 fabric. And what we're able to do with that is divide up the resources in that fabric, giving different resources to different research projects. Because, again, GENI is an instrument for research in our view, and that's what's being done here. So the different colors are different researchers doing different projects using different slices of the domain, using interdomain principles. These are different showcases done at the last few SE. So that's our model. We want people independently to do things, not to go supplicate for resources from a central NOC, not to beg resources, but actually to find resources, stitch them together, use them, and move on. This is our prototype SDX, which you saw a bit of a demo of this morning, connected to the prototype SDX in Atlanta. And essentially what it is, despite all the boxes and lines here, it's a virtual switch. So imagine, if you will, a virtual switch that acts as a capability that can be highly segmented, partitioned, giving different under policies, resources to different communities, and then under it supported by lots of other switches. What they are and what they do sort of doesn't matter because you can swap them out. What matters is that architecture for that domain. We're doing this at the Starlight facility, and I'm going to point to Jerry Sobieski. There's been a project called the Glyph Auto Goal, which is doing this at a global level in a very nice way. The NSI project has been developed as an API to different control frames in different exchanges, different countries. Since Jerry's talking about it, I won't say much about it. These are some of the VLANs that are out there. This is quite a nice project, and that's an ad for Jerry. So thank you. Questions?
I worked on the auto goal on some of the early stuff. Jurgen van Malmenstein is heading it up now, and he is the guy who generated that last slide. You know, under his tutelage, all those VLANs. So he's taken that much further. No, I would just underscore a couple of points you made up there on one of the early slides about all the issues there. I think one of the biggest issues we're going to run into with the SDN exchanges is the notion of resource discovery and advertisements and topology. representation and distribution. Those are terribly hard problems.
Right, so that's the key issue in a software-defined networking exchange, and nicely summarized. Basically, an exchange is an exchange of resources. Domain A has to say, these resources are available to domain B under these circumstances. That has to be instantiated. And also, you need a description language. You need a semantics and an ontology. Some very nice work has been done by the network description language folks at the University of Amsterdam and the OWL extensions at RINSI. But that's the critical piece, because that's what it's about. It's about that conversation between the person saying, I want these resources at this time, and another person saying, this is what's available at this time. That's the key. That's the middle of it.
Well, I would actually say there's another step in there that people kind of just blow past, is the fact that there's actually, the sequence you described is a negotiation process, right? Whereas, I think if we wanted to really start, the most simply would be to say, look, the researchers got to have some idea of what they need. Just ask us for that, and we can tell you whether or not that's available. And then as a second stage, go to the process of negotiating with a provider to see what they have before you ask them for what you might want.
Right, and I'll also say that it's key that this is oriented to an edge process, an edge application, an edge individual, an edge organization, asking for things and getting them without talking to the central NOC. We want to get the central NOC out of the middle.
And also, I think, is the ability to broker for those edge systems, right? So that you don't have to, the user doesn't, if they want to, they can, but if they don't have to go talk to every network around the world in order to get a global reach for their slice or their experiment.
Absolutely.
Someone's calling in with a question.
We take calling questions.
Other questions from the room?
Okay.
No? Okay, thank you, Joe. Our next presenter is Inder Manga from ESNet, who you all were introduced to if you were at the plenary by virtue of his picture. Yours should work.
I wanted to see how many acronyms can I fit together in the title. Multi-layer, multi-domain, SDX, everything's in there. I can talk about anything that you want in the slides. In any case, I think one of the things that I just realized was that even like any three-letter acronyms in networking, this one also has many definitions, SDX, just like SDN has. So it's going to be interesting. Is software-defined exchange an exchange of resources? Is it an exchange of traffic? Do these two equate to each other? I think these are some interesting debates we'll have, or we should have. So let's talk about multi-domain SDN first. What do I mean by it? So SDN so far, I think in most, I would say, popular literature, presentations, vendors, they talk about the control and data separation, but they really, truly ignore what happens if you have two controllers that don't have the same administrator. So they talk about two controllers as a logical controller, but they never talk about two controllers handling separate policies and how do they interact. That has been left unsaid. So it's a control plane within a single domain, a data center, a service provider network, campus network, but they don't really talk about. So that's kind of something that has not been addressed at all. And it has not been addressed maybe because the popular vendors don't see that as a requirement, or popular data center operators don't see that as a requirement, obviously don't. Or it has been left to IP routing and saying, well, most of the traffic is IP, so if you want to go across domains, go across domains like you go today. You use IP and that's it. So why do you need multi-domain? Okay. And I think my conjecture is that if you do that, if you let it be IP, then the whole end-to-end flow issues of today, QoS, packet lost, are not solved by SDN by default. This is what this community has been doing as traffic transits multiple domains. So when you hand over the traffic to another domain, it is gone. And you don't have any control over it. It's a black box. All you kind of hope and wish is it gets there in certain decent latency. And if there is packet loss, then hey, God forbid, you have to call someone else and figure out if they will fix it or not. So that's kind of where we stand today. And is this okay? If not, then we should work on that. So I'm going to talk about multi-layer and what does that mean in this SDN world. So this is the OSI stack, layer 1, 2, 3, and you can go all the way till n, 7 being the more popular value of n. And there is a management plane that kind of manages each layer, and I've kind of just built some partition in that because the optical management layer may be different from the layer 2 and layer 3 management layer. So how does multi-layer work in an SDN world? This is what I say. I mean, you get a network-wide cross-layer view when you separate that control pieces out from each layer out to the above layer. I mean, this is all things that you know. It's just I'm repeating it so that we are on the same page here. Now, obviously, OpenFlow is one of the protocols that has been used to control the layers. And I didn't put OpenFlow for layer 3 because one of the ways we think layer 3 can be, it can be an application. So all you need is layer 1, 2, and you can make layer 3 an application of this SDN-based network. So one example I will give you of a multi-layer demo we did very recently with Infinera and Brocade, where you can build an application, host traffic going from host A to B. They are the IP-aware hosts. You have the typical routing pattern where packets go from router to router to router. They are IP routed. And with basically based on traffic detection, which you can do based on your traffic optimizer, you're getting statistics on a per flow basis. You can decide when the flow needs a little bit special treatment, a little bit of a shortcut. And I don't know, whenever I step on this wire, this seems to blink. So anyway, so in that case, you can do what is popularly known as an optical bypass, talked about a lot, never automated, but manually done in carrier networks today. So this is SDN can be used one way to automate optical bypass on a flow-by-flow basis, not necessarily on a port-by-port basis or a customer-by-customer basis. So that's kind of one of the things you can do if you follow the previous SDN-based architecture. So again, talking about software-defined exchanges, because that seems to be the topic of the day. I'm not going to dwell a lot on multi-layer or multi-domain. But software-defined internet exchange was a paper written by folks that you recognize, the names here. It was presented at Open Networking Summit in 2013. And I think you have heard Russ Clark in the morning. So he's one of the authors of this paper. It was one of the first papers written on it. And we at ESNet have been collaborating a lot with Josh Bailey, who's one of the other authors on it. So I'm going to present some work which has been done by us and working with him and his software. So what is the motivation to do SDX or software-defined exchanges? So most of the popular SDN deployments are mostly layer 2. People are doing VLAN manipulation, bridging things from one place to another. IP is interesting, but I'm not sure how many people use IP-based flow mods for really routing IP. There's a lot of VLAN addition and translation slices where you use IP addressing to separate, virtualize and separate slices out. But that's kind of what I believe the more SDN deployments are. So the question comes is, if SDN as a movement has to gain momentum, should you beat the internet? I mean, this was designed as the future internet architecture. So do you need to beat it? So you need to replace it? You need to go faster than internet so that eventually you dwarf it? Or can you join it? So to me, software-defined exchange is a great practical way to join the internet. So what you do is, you ensure your SDN islands can peer with the IP network of today and exchange traffic. And you can exchange traffic between SDN islands as well. Now, I put a double star here because if you just exchanged IP traffic between SDN islands and you would defeat the purpose, then it is back to square one, as I talked about multi-domain. So I would say, what I'm not calling it a tagline, but it became a tagline, is go with the flow. So opportunity exists to do flow-based exchanges. So you can have an application-based exchange, you can build a ROC-based exchange, which only exchanges RDMA over converged Ethernet traffic. You could build an exchange for a certain flow type, and not just an IP traffic exchange. And you can have policies and procedures and routing just to do that. So that's what I see the power of SDXs in addition to what the internet exchanges do today, because they only exchange IP-based traffic. And this is not the full multi-domain picture. I think there's a lot that can be done, and SDX is only one piece of the multi-domain picture. I think what Joe said was kind of the overarching, how can you exchange resources at this rather than just traffic, and I'm just sticking at the more practical. Let's start with exchanging traffic, and then we will figure out some of the challenging topological and other representational issues to exchange resources. So in our journey with SDX from an ESNet perspective, we did a demonstration of what we call frontline assembly. And the name is very appropriate. What it says is, your routers are your frontline, right? When you peer with other people, that's your frontline. So how can you take a router and disassemble and assemble an SDN-based router, which is based on a simple switch and the architecture I talked before, which is an SDN controller and routing on top. We built this with Josh's help, and we peered with RIANS, which is another research and education network in New Zealand, which I'm sure all of you know who's leading that right now. In any case, we built this and we put actual routes and traffic through it. Chin had a lot to do with drawing this diagram and configuring and making this up and running. But we ran into limitations. The limitations was the switches don't have a lot of flow space. And if you talk about routing today with 400, 500,000 routes, or if you listen to AT&T with 4 million routes, there is no way you can build a capable router with those kind of things. So one of the good things about SDN is, hey, fib compression. Hey, there is an algorithm, go implement it. You didn't have to wait for the vendor. You didn't have to do a feature request and wait 2 years. So we implemented fib compression, and we could say that you could get 40% more space by using fib compression. So this was kind of interesting. It was a good kind of indication, hey, this has got some legs. Let's investigate this further. So I think this is the detailed picture. Heidi wanted some detailed pictures, so this is there. So then I think there's another picture drawn by Chin. We went to something called the treehouse, where we said, we're going to try to build an infrastructure with BGP peering across multiple networks. So right now, New Zealand and RNet are on it. There is also different universities coming on in New Zealand that are peered with it. There are promises by a lot of other people around the world in Cambridge and US and South Africa that want to get onto the system, but they have not had the time to build that up yet. So that's kind of one of the things you're doing. And I would like to ask you, if you run a campus or a network and you want to peer BGP and get some experience, small number of routes, put some traffic on it, if you want to do that, you can join the treehouse and be a branch on this tree. So we're looking for more and more people. My goal is to get a BGP around the world, and maybe Joe can help me with that. This is the SDN testbed final plan. Not all components are installed, but we are building a nationwide OpenFlow testbed. Heidi wanted some testbed stuff, so this is for your thing. This is different from any of the software-defined exchanges stuff. It is our internal testbed to prove out some concepts and features and services that we want to do. with SDN and deploy it and offer it for our customers, which are essentially big science sites and for science traffic. Anyway, yeah.
So some of those sites are also places where XOGeni racks are going, right?
Right. So one of the site, NERSC, is where XOGeni rack is going, and Brian is here who right. What I meant was some of the DOE sites. Starlight is Joe Membretti. So Starlight and NERSC have 40 gig XOGeni sites, and you can get 40 gig between them as soon as you figure the interface thing out. I think that still needs to get figured out. But as soon as we get that figured out, you can do high throughput GENI testing with OpenFlow and reconfigurable infrastructure. There is 10 gig connectivity, I guess. I think either Brian or Rick can confirm that. Yeah, Brian is shaking his head, which means we have 10 gig connectivity between the XOGenies right now, and you should feel free to use it. And I mean, I think that's one good part about federation and federated infrastructure. You can get a lot more than one person can deploy or use. And I think that's a great architecture to go on. I'm going to jump back into SDX and actually use some slides from an ISP in New Zealand called CityLink. So they have been on this OpenFlow-based exchanges as well, and they run a real IXP. And what they say is that the current IXP is, it's this whole exchange layer 2 exchange traffic, and what gets exchanged, that hygiene, is based on trust. You trust other guys to do the right thing, and if they don't, and there is known when they're done, people are stealing bandwidth, stealing packets, rewriting their MAC headers to get traffic go through, sending LLDP packets to probe what the other guys have as equipment, and there's a lot of bad behavior that's going on that the exchange operators are worried about. They don't tell everyone, but they are worried about. And I think, so what are the things they are going, and as an example is, they're putting SDN on the top of their IXP, where the forwarding policy is embedded in the controller and not configured by everyone on a trust by trust basis. And if you look at this, this is what becomes, so there is some static routing and static forwarding policy, which is base router hygiene, and then you put dynamic forwarding based on requirements, they have a web-based interface into it where somebody can say, hey, I want to exchange traffic now, and it automatically gets put into the system and it works. So that's kind of one of the things their vision is and they're building, and it's very encouraging to see the commercial sector down this software-defined exchange movement as well. Now, the customary cartoon, everything is software-defined nowadays. So I'll leave some food for thought for all of you guys. So one of the things is we need to learn how to build software-defined networks that can interoperate with the existing internet. I think that is critical. I think we build islands and we show demos, but that's not going to move it further into operational, further into deployment. We need to figure this, how to best interoperate an SDN with an internet island. It could be using SDN-based routers. It could be using SDN-based exchanges to exchange traffic. Not do it the traditional way, but have to figure out how to do it with the software-defined networks. One of the other things is you cannot have capable SDN without capable hardware. One of the biggest blocks for us on software-defined exchanges and ramping that up has been the hardware. We don't have capable hardware that exposes things other than buying a real router from a commercial company and putting it there. That can be used for this. So we are looking for and waiting for capable, I wouldn't call it white box, but capable OpenFlow ready, OpenFlow enabled hardware so that we can build, expand on this capable software defined exchanges. And again, what I meant, which I'm repeating, is the capable hardware today is not pure SDN. It is what the routers are building their current solutions on, and when they give it to you, it comes with all the software and all the restrictions. So they have different TCAMs for IP forwarding and for layer 2, and it's hard for them to integrate. The silicon is not there yet, the forward looking, and that's kind of one of the things that are inhibiting wide deployment of these SDXs. So SDX brings the need for all three to get together, which is interoperate with the existing interpret, need capable hardware, and you can do pure SDN stuff with it. So it's challenging, but fun. And I'm excited that at this GENI conference, there is so much discussion on it, experiments, and interest in moving this forward. Thank you.
Okay, thanks, Cinder. That was very interesting. Next, we have sorry, Jerry Sobieski from Norgenet, speaking about European testbed experience.
Everybody can hear me? All right. Well, thanks for this opportunity. I'm going to talk about the testbeds as a service. This is in Europe. The GENI network is the pan-European network. It serves 40 plus nations, and it's the R&E. It's the core R&E network in Europe. And they structure their projects a little different than they do in the U.S., but there's a project in part of GENI Plus, the current rendition of GENI, called SA2, the Service Activity 2. And it's about testbeds. It's called Testbeds as a Service. So the premise was, you know, it's finally become obvious. We need some place we need some sort of crash test dummy to pursue our network research. And those networks that do this, we have to have certain characteristics associated with them. This is just a quick list of things like stable infrastructure, high-risk experiments. They need to protect the experiments from other experiments. Jerry, I can't really hear you. Oh, it fell. Sorry about that. How's that? Okay, good. All right, so the network R&D, this is preaching to the choir a little bit, but these are some of the characteristics that we defined for the testbed service in Europe. Stable underlying infrastructure, high-risk experiments. We wanted to make sure it was insulated so that what we did in one experiment wouldn't affect other experiments or wouldn't affect the production network. Needed to be reliable so that the experiments could be run reproducible and such. We wanted a broad range of opportunity here also. We didn't want to just focus on one technology or one particular flavor of the moment. So it's quite extensible. It's scalable. We want to make sure we can do big experiments, global experiments. And we want as much as possible for these to replicate real-world scenarios. So they defined this project TAS. They asked me to head it up. It's basically got three components. There's a dynamic, we call it packet test beds, but it's really just virtual networks where we allocate, this is probably as close to GENI as anything else, but we allocate virtual machines, virtual switches, virtual circuits, according to a user-defined topology. Let's see, we have a dark fiber test bed that's a little bit, it's kind of the orphan child. We needed some place to put it. We had some fiber, so they said, well, let's give it to the test bed guys. And so we're offering that to some of the European photonics and physics guys for some experiments. And then there's the GOF, what we call the GOF. This is the GENI OpenFlow facility. This was built by Aphrodite Savesti and her group in one of the research projects in the previous version of GENI. And they got it up and running, and then the project ran out. So we're keeping it going until the TAS software is all ready and we launch, which should be fairly soon. But I'll talk a little bit about the golf, because that's actual OpenFlow testbed that we have running and operational right now. This is a production service. This is an experiment. You know, we have 24/7 monitoring. We have a NOC in Cambridge that monitors the equipment. We're building a very sophisticated operational, as Luke was referring to, some of the internal operational monitoring agents and state that we have to track. So how does it work? We view test beds as just graphs, right, with various forwarding elements in them. Those could be switches, those could be virtual machines. Almost anything that actually does some thinking and makes some decisions on the data it sees. And the other part is just transport links. These are virtual circuits. All they do is move data. They just take information, take it from one location and deliver it to another location. We transfer that graph into what's called a resource graph that basically says the network links, the network computational elements, all these are considered resources, and all we have to do is just define the relationships between those ingress and egress ports. So these data flow ports, this resource graph is actually lends itself to doing validation, making sure that the ports are matching each other, that when the user configures this topology, it will actually go together. How does it work? Well, this was the great idea, right? The researcher has some brilliant idea. He comes up with a concept that he wants to see deployed. There's a GUI that front ends the whole task service. Now, this is just a user agent. So in the long term, this could be a user application that's going and talking to the service and asking for these topologies. But the user defines through this GUI or through a CLI a domain-specific language. We can describe the network topology that the user wants. And then that gets fed to the resource manager, which is an agent that runs in the GENT core backbone. And it goes out and finds all the virtual machines it needs and places them in the service of this user, sets up the virtual circuits between them, and then passes the whole control over to the user. So there's still a proxy that we have to go through for certain functions for the user to reach these components. But in most cases, the user can actually log into these components and do with them as they will. And there's a cycle here. So the user can modify this on the fly. He doesn't have to tear it all down to add new links or new nodes to it. This slide wasn't quite finished. But what we have is along the bottom here, we have various different types of infrastructure. These are the storage facilities, compute nodes, virtual circuits, anything that we would look at as raw materials from which we can build these virtual components. Then those are fed through a number of different layers of software. It could be different packages. OpenStack, we use OpenStack for the computational nodes. Junos or the HP switch, these are just the interface on the switch units themselves that we use for virtualization. There's the NFS and OpenNSA and the other GENT service called Bandwidth on Demand. This is roughly equivalent to the Oscars style services you see in the US. So the OpenNSA aspect, I'll talk more about that in a second, but that is going to be how we're going to get out to the rest of the world. So this raw infrastructure is used to build dynamically construct resources or put some resources on the shelf that we can just pull off. They're already initialized and much faster for setting up circuits, setting up the environments. And then the last thing is there's these agents up here on the right, the control agents. These are the users when they're getting in, they're sending some commands into the service to reserve, activate these elements. So the common denominator here is all these resources have one of these five, have to implement these 5 primitives, and those primitives, and they can implement more. They can do other functions, but they have to implement these 5. And this basically allows us to cycle the components through life cycle. So we can reserve it, we can activate them, we can query them, we can deactivate a resource, we can release it. And it's maybe not real obvious here, but we can build composite resources. So we can define resources that reference other resources. And so we see this as a way this is all going to scale up and allow us to do simulations of much larger networks. The current resources we have out there right now, of course, there's a discussion amongst a number of people. I'm getting it from different sides about harmonizing resources between what we're doing in Europe, what's being done in the US or in other parts of the world, in South America or in Asia Pacific region. The processes, the resources we're going to offer first are virtual machines, virtual OpenFlow fabrics, and virtual circuits. Those should be delivered and operational in the next 30 days in several nodes in the core backbone. And then we'll add to those over the next few months. Virtual routers, there's an intent to deploy OpenFlow capable routing instances on the Juniper core backbones. Bare metal nodes, we'll be doing some other things a little bit later in the year, providing raw spectrum. We're going to try and figure out how to do photonic test beds, which has a different resource model. And then there's other resources that we want to define that don't necessarily have a physical analog. They may be functional things like an IP subnet to access all your devices in your test bed, which includes IP routing, virtual VPN servers, DHCP, or other types of support services within that whole resource. So how does all this kind of some high-level views? We have different test beds all come out of the same infrastructure pool. This is an interesting one that I wanted to point out, because when we talk about interoperating the data plane from Europe to either the NRINs within Europe or to other networks outside of Europe, this is how it's going to happen. We have each of these test beds, they're self-contained. They have ports defined inside the test bed, but we can also define ports that exit the test bed, external ports. And this allows us to monitor very closely what this experiment might be doing that could be perceived as a threat or a risk to other services. We can provide general internet access that way, or we can use an intervening NSI service, for instance, to build a circuit between testbed islands to just link them up and essentially turn them into a single island or a single domain. This is looking at it just a slightly differently. If we have, and we're going to be headed towards this way, I think, later in the year, the multi-domain issue. The way we're viewing it is if we can get resources from any provider, we don't really care. The provider shouldn't really care what testbed it's in. That's a higher layer function. We will be able to track the stuff, but fundamentally, it's the provider is going to give us some resource or some subset of resources, and the user is going to be responsible for maintaining that within their network. So they can get these resources from any provider. Providers could get them from other providers if they don't have them, right? So this is, I think this is the way we can scale some of these environments up to global reach. So the current OpenFlow facility, this is operational right now. It's been operating for about 9 months, maybe close to a year actually. It consists of 5 sites: London, Frankfurt, Zagreb, Vienna, and Amsterdam. And they have a Sun server in there for compute nodes. And in Frankfurt, we also have each node has a compute node server and a vBridge server. So we can do the virtual switching at the nodes. They have a 1 gig circuit in between them and a full mesh, and then Frankfurt has a controller in it. And as Luke was referring to, or someone in one of our previous talks, all the flow spaces are signed manually. This is it's limited. It's usable, but it's not the long-term solution, right? We can do as good as it is and as noble an effort. We need stuff that scales better. And so once this is up, All right, this is the TAS solution. We're going to migrate those OpenFlow devices into TAS. You should actually, now the TAS, I mean the OpenFlow facility now, it's all software, software OpenFlow, right? So when TAS hits the streets, we'll have hardware. We actually have HP 5900 switches in there. So we're going to install in Copenhagen tomorrow, actually, tomorrow and Thursday. Then Bratislava. Some of these first sites we chose not because they're great connectivity, but because they had space in the pop, right? So we have to make a balance here. So in Copenhagen, Bratislava, Amsterdam, Ljubljana, and then we have to see what the migration will be, whether we start eating the OpenFlow facility now and moving into places like Frankfurt and London, which are at capacity space-wise, or whether we go after some of these other sites first, like Paris or Geneva or Athens, right? But in any case, the point here is over time, we will see the same architecture. It's roughly, think of it as a GENI rack, right? That goes into each of these POPs, and they're linked together. We control it from servers in Copenhagen first, and then we'll double that up for redundancy. Yes? Bratislava, yes. Close your eyes and imagine this. Yeah, it's not in the near future. Moldova, maybe. This first 4 sites will have 10 gig connectivity, full mesh amongst them, and 10 gig from each site going out to the GEONT, so we could reach that 40 gig in some combination out to the US or to South America or to Asia Pacific. So we will have good connectivity here, and that's going to increase over time. The way we do reach out from this, we have the various sites in Europe, and we have an infrastructure within SA2, within the TAS service, that allows us to reach between all these different nodes. But then if we need to go outside, it's very easy for us, because that internal service is an NSI-based service. It's going to appear with the bandwidth on demand, which will be NSI as well. So they'll just fall into place as long as we deploy a consistent NSI architecture globally. Going from any one of these virtual components within TAS should be just a matter of making a reserve statement into NSI to someplace elsewhere in the world. So, I think it's one of the beauties of NSI is that it's starting to come out and starting to really lay that base down that we've needed for years, and we're starting to be able to take advantage of it. So finally, interdomain, multi-domain. We're exploring a strategy right now. It's time to start the discussion, certainly with the US, and frankly with the entire community globally, about not just harmonizing the resources, but harmonizing the service semantics and the protocols we need to do this across domains. We have 8 different ways of doing it. There's the Dilbert cartoon that says that we got 8 protocols here. We need 1 protocol to unify them all. Now we have 9 different protocols. So you have that risk. But I do think we need a canonical form. I do think one of the ways that if we want these types of experiments, this type of testbed world to scale, we need to have a canonical form. We can't keep trying to write translators that talk to that framework, to that framework, to that framework. We just need that one central form that everybody agrees to support, at least on the intradomain basis. Whatever they do inside, it's up to them. But this allows us to reach around the world to do these things. We've seen this pattern before. We certainly see it in early routing protocols. We see it in BGP. We saw it in NSI, and I think we'll see it here too. So where are we going? The TAS 1, we want to show the first demo by April 1st. So it's going to be right around that time. We're shipping equipment right now, and we're trying to tie up the loose ends. Version 2 will be probably after the summer, after everybody gets back from holiday. We'll probably finish that up. That'll be mostly just adding some more features. One of the interesting things that I think is important here is the cloud data center integration. One of the reasons we use OpenStack for the VM management was so that we could reach into these data centers that the universities are creating and use those to grab VMs. I mean, that all of a sudden increases our ability to get testbed networks from a few dozen nodes up to hundreds or even thousands. So we want to pursue that over the next 6 to 12 months. Multi-domain resource brokering. And then as GEONT 3 Plus winds down in Q1 of next year, we should deliver TAS 2. And then immediately after that, GEONT 4 is going to start up. And GEONT 4 is going to start with a 1 year where we've already put in our requirements for funding for that 1 year, which basically doubles everything we've done so far. And then GEONT 4 extends another 6 years past that. So in Europe, we're coming up to a big junction here where we're really putting resources in place for the next 5 to 7 years. So this is important. These are the conspirators, all the various interns in Europe that are helping on this project. And these are my guys that are actually doing all the heavy lifting. Blaise, Peter Zegedy, Fabio Farina from GAR, Dom Taylor at Dante, and for some of you might know Mikhail Heslinski from Chestnut in Prague. He's taken over T1. So that's what we're doing in terms of test beds and a little bit about how we're trying to reach out, trying to open it up to a global access. Questions? You.
Jared, how much do you see SDN influencing the design of next GEOC?
Repeat the question.
Sure. My question was, to what degree is SDN influencing the next design of GEOC that's underway?
I think SDN is going to have a big influence. It's not clear how OpenFlow specifically will play into that. I think the notion that we have programmable virtual networks is just unavoidable anymore. I think actually that's the best way to go. I mean, it's going to solve, I think it's going to be the basis for a lot of issues, everything from just flexibility to security. If we can move our networks around easily, it makes it very difficult for people to break into them, for one thing, right? Makes it easy to grow things. There's a lot of value to virtualization. So I think that aspect is all software related, right? So I think it's going to have a major impact.
So is there a preferred protocol alternative to OpenFlow that you guys are looking at, or it's just saying that there is a software layer that programs the network using whatever existing protocols exist?
Right. It's not saying, it's just kind of trying to be technology agnostic. We got to have programmable networks, right? Whether it's OpenFlow or whether you use something else, it's whatever's convenient and appropriate at the time.
It limits what you can program.
What?
It limits the scope of what you can program.
Yeah.
So I mentioned NSI and didn't say a lot about it because I thought you would. You mentioned it but didn't really define it. And there
Well,
might be some
you got to
people
come to the next session.
There might be some people in this room who don't know what NSI is. Maybe you could
Okay,
give the
so I'll give you the elevator speech. That's 30 seconds.
Three-sentence version.
NSI, the Network Service Interface. This was one of the community projects in networking, started about 4 years ago. And it's basically developed an interdomain model for connection provisioning, right? The nice features about it is it does not dictate how things are done internal to a network. It lets that network decide how they want to engineer it, what kind of software they want to use for provisioning. But it defines a standard for communicating the service semantic across domains. So we can, and it basically has the same 5 functions there: reserve, a provision, a query, a terminate, and a cancel. So you can set up a connection any place in the world, give it the 2 ends, tell it what you want in that connection, and it'll communicate that request across domains. That's something that's been missing because one of the key things is that it doesn't try to fit it to a particular technology. It lets you define what those interfaces are at the edges, where you peer with another network, and announce those so people can kind of see the topology, the global domain topology, not the specific, not every patch cable and everything. But it lets you give a high-level global topology, and then you can decide how you want to progress your circuit through there.
So another bit is it's actually developed as a standard
Yeah.
by a standards organization. That's a key feature in this
Yeah, this isn't a
world of-
research project. It's being deployed in Europe, in GENI, as part of the bandwidth on demand service. Several other networks in Europe, certainly Norgenet is deploying it, SurfNet is deploying it, Pioneer, I believe. We expect to see it in the US with the Oscars module Luke was referencing, and ESNet. And we've got participations from Kudo-san at AIST in Japan, and the KDDI folks in Japan and Korea. So I actually have a slide here someplace, that shows, oh, there was that slide, it got moved. Nope, I guess not. It's in the next presentation, where I have a picture of the world of the AutoGo, right, with all the different sites that are actually using NSI around the world.
And unlike many research projects, this is fairly well documented.
Yeah,
which
I mean,
is
it's in
rare.
version 2 right now. There's a how much, 40-page standard that describes it. We got to simplify it. But it's there, it's being deployed. We've done experiments on it and demos on it for over 2 years. So I think this is, I think this is going to form that basis that allows us to put circuits up dynamically, either on demand or scheduled with guaranteed performance, in a matter of a few seconds, right? So this is a big step forward, and I would encourage the GENI community to look at it closely, right? I think it's really going to help you a lot. And it'll certainly increase your reach. Rather than having to nail together all your circuits everywhere and having to know all that information, there's actually a service that's coming into play now where you can pass your request. I want to connect to that node on that server on that VM in Moldova. And we should be able to get it there. Inder was one of the co-chairs, Tomohiro was one of the co-chairs, and Guy Roberts. So talk to any of them if you have more questions, or me. I'll point you at them.
More questions? So I have a follow-up question. We have Starlight, ESNet, and Internet 2 here right now who are supporting NSI. We have you who's supporting NSI. One could imagine that we all got in a room and, a couple months from now, we made the agreements to say, yes, we're going to peer and allow these connections. Your testbed seems a little different in that you are investing a lot of effort into the tools and access directly to the experimenter and communicating back to the experimenter what happened, which is a whole different level than just setting up the exchange. So how do you envision when a GENI experimenter who you don't know is able to somehow request through GENI stitching the ability to connect to one of your test beds or vice versa, but there's no infrastructure for talking about it succeeding
The way that
or
we'll
not.
get to the SA2 test beds is there's this core resource manager. There's a protocol, right? If you want one of my VMs, you send a request to that VM. It's authorized just like anybody else, right? You just let us know if you want to play in our sandbox. Let us know. Initially, we're going to open this up so that for small test beds, it's anonymous. You can just log in, right?
Okay.
Then there's an intermediate level that we have that will require you telling us who you are. And we may still put some limits on how long you can hold the test bed and how many nodes you have, because we're kind of constrained on the actual physical infrastructure. And then we have the cognoscenti. These are the guys who may want to actually create new hardware and put it into POPs and virtualize it and make. When I say virtualization, I don't necessarily mean you have to partition it up and serve it to everybody. But there has to be a way that you can put it into the system so that we can allocate it properly. We can control it and pull it back when we need it, reinitialize it, take it out for maintenance, do all the things you have to do to production service.
So,
Right,
in that first stage, there'd be opportunities for people who were in GENI, if they wanted to do international collaborations, they wanted to do tools,
Yep.
monitoring, whatever.
Yeah, there's some glue we're still trying to get together with the NSI stuff just to get that to work over our network with our pathfinders, and then it'll peer with the BOD service. So anybody who's peering with the GENT BOD service will be able to get in at the data plane level. The control plane is just, there's the web service, point at it and go. Now, right now, the way we've set up TAS in this first version is that it kind of just looks at its own resources and says, that's me, right? What we have to do now is, once that's running, we'll take the next step and say, right, how do we stamp the same service out into multiple INRENs in Europe? Right, it's the same service semantic, it's just different resource sets, right? How do we, make that happen? And then the big question is that we have to start right now also is how do we do the intra-domain stuff? Is there it's this common canonical model for testbed services globally that we need to, because I guarantee you probably 2/3 of everything we've done in here, maybe more, has analogs in what the GENI community has done, right? There's, we probably called it something different. Just, it's probably something in Polish, right?
Yeah.
But the fact is that, that great minds think alike, right? There's going to be a lot of similarity between you. So if we can get those together, find common terms, and where there's some differences, compromise and find a common model, then all of a sudden this stuff will just start falling into place and we can build networks wherever we need to. Frankly, I think that's really important, much more than just for the network research community, because I think the same technology will be used by the applications community to build virtual networks to test how they want to deploy networks for their applications, whether it's physics, whether it's the EVLBI, the radio astronomers, or the genetic repositories that are being built. These communities, they're wondering how do we build a network so we get the kind of shared repositories around the world and access to our workflows that we need. And so being able to build virtual networks that have those performance guarantees and the repositories at the endpoints and all the components they need, that's a very powerful end game here.
Yeah.
And it serves much more than just the network research community. So that's kind of where GENT's looking at it. They're kind of looking at this bigger game here, that this is a great way to get started. It's a necessary way to get started. But there's a bigger end game. Yes. Yeah.
Jerry, if I got this correct, you're looking at deploying these test beds at these different nodes in these various countries.
Call them pods.
The pods, okay.
Pods.
Where are the pods physically going? Are they going into like telco colocation space, or are they going to some other?
They're typically going into telco pops. There's what is it? Harbor Exchange in London. There's the pop in Øresund and outside Copenhagen. These are real telco pops.
Okay.
Because these are the GENT core pops, right? The cages, right, that GENT operates.
Okay,
right?
yeah, I was wondering about that. Here in the U.S., anyway, we've had a lot of difficulty with space and power in that kind of facility, and so there are well-connected facilities here in the U.S. where I try to
tell you
do
all kinds of interesting stories in private.
Yeah. Okay.
But you're absolutely right. So we're not putting a whole lot of resources or infrastructure into the pops. We just don't have the space. If we want to have some place where we might have a big blade server or something, there's opportunities to co-locate those with some of these pops. Like in Prague, it's very close. It might even be in the same building where the GENT pop is and where the local INREN has their facilities, right? So that's obvious. In some places, there's fiber from the pop to a local university or something. We can do things in that respect.
Okay, so you'd sort of do the same kind of as with placing
Yeah,
stuff in a regional here in the US.
The,
You're looking
the
at placing it in a node.
SA2 project, right, which is the core network, we want that co-located with the other core equipment, just so that all the NOC and all the procedures and access and
Yeah, I understand
field
that.
and hands and eyes and all that stuff works in the same model. But when you look at the broader community service, we're going to be putting these in the NRENs and their POPs, and there's, some of those are co-located, some are distant. But you're going to have more flexible spaces to work there. And in theory, other than maybe some latency issues, these university facilities, pods, or in more flexible spaces would be probably a place where we can really build up, get cheaper power, more space, easier access.
Okay, thanks.
Any more questions? Okay, thank you, Jerry.
Thank you.
We have another person who's working on providing testbeds as a service in Brazil, Aira Mercado, from RNP. I don't speak Spanish, so I won't try to pronounce it. Oh, Portuguese, I'm sorry. Even more embarrassing. Well, now that I've insulted our speaker, I'll shut up and let you tell us about your plans. Machado. It's right here. Do you have one of those or not?
Okay. Are you hearing me? It's okay.
This is not coming up. I haven't changed anything since the last time. Oh, that's the one that was doing it?
Oh.
Can we have some AV help up here? It's the same. It worked for Joe's.
Yeah.
So. Oh,
Okay. I think that's some. Okay.
we
Okay,
go.
there we
Okay,
go.
thank you. Yeah. Yeah. Okay. No, I didn't
Oh.
touch it. I just put it into the slideshow.
Okay,
We're
okay,
fine,
okay.
we're fine.
Yes, moving
Sorry
here.
about that.
No, okay. So, thank you, Heidi, for the invitation. It's very nice to stay here. I talk about what will happen in Brazil in terms of the SDN. And this is the fiber project. That's the project that's funded by Brazilian government and the European Commission. Is a project to create a test bed in Brazil and enhance a test bed in Europe and federate all the test beds. The start is project in 2011. Is the university that participates of the project. Is a lot of university in Brazil and university in Europe. And you have this scenario, island in each institution, so you need to connect all islands. Let's explain. In fiber, you are using two kinds of the control framework. One is CMF, is a control framework developed in the Ophelia project that control OpenFlow equipments and server, and the OMF that control wireless equipment. You have the GENI because you have a cluster MLab in São Paulo. So you decide to use the three control framework in the test beds. And this picture shows the institution, the control framework that you deploy in the island, and you have more WDM GMPLS, one in CPKD and another in Bristol. That's research that participate of having the test bed. In terms of the connectivity, you have two links, one from Bristol to São Paulo, and another from Ituquete to São Paulo. I show the next slide in more detail. And you have two VLANs connected from Internet 2 and Rede Clara. In Brazil, you decide to connect all the test bed, create an overlay network on top of the production network because, unfortunately, you don't have an infrastructure separate to experiment. You have to use the same infrastructure. Here is a picture that shows a typical fiber island. And one island in fiber has OpenFlow switch that use Pronto, IBM server that virtualize and has a lot of the VM for the experimenter, and VM that support the application. 3 net FPGA server, and some Icarus nodes that support the wireless experiment. In the island, you have an equipment atop of a rack, is a Datacom, is a company in Brazil that supports OpenFlow. That's not used for create the data plan and the control plan. This equipment connects with another equipment Datacom in the board of our network RNP. Here's more detail about the island because you create the data plan and control plan inside the island. So you connect all the equipments with 2 networks side of the island. And on top of the island, you have a switch, and another switch is on the point of presence of the network. And to structure all the islands is homogeneous because you start from the scratch. Everybody follow the definition. That's easy to work in operation. So, FiberNet is a network that creates on top of the production network, is an overlay network. And the idea is to integrate all the islands of the project. And the requirement that software fast and secure way to build experiments. And in level 2, and level 3, because wireless is a level 3, and the two kind of media, wired and wireless. So it's SDN based because it's programmability, virtualization, and it separates the two planes, the data plane and control plane. Here's more detail about this network. So you have a cluster, as you have in GENI, one island. The concept of the island is the concept of the hack. So you have many aggregate menus in one island. And each island is in the laboratory at a university in Brazil and connects this island until the backbone of the RNP. And depends on the institution, you have a metropolitan network between the university and the backbone, and some island, some institution is close off the POP, so you have a fiber, optical fibers. They had a lot of difference last mile. Yeah. So now we have 6 point of presence, 6 POPs that participate of this network, and the idea is extended for all the backbone. G-Fabric Next, so you have it's two overlay network. The data plan uses static VLANs that you create a full topology that connect all the university. Is a point-to-point. To control plane, you decide to use a VPLS cloud because you need just connectivity, and it's a multi-point network. So we have two networks. And this picture show Pará is a state in Brazil, is a point of presence, and you have is the Juniper equipment, that the production network equipment that connect to Datacom is a OpenFlow equipment from the backbone of the SDN, because the SDN for us is an overlay network. So you have the concept of the backbone SDN and the backbone, the level 3 IP, blah, blah. So, and the ilha, no, in Portuguese is island. The island of the University of Pará connect with this equipment in the POP. And it has two equipments. The Pronto is the PK8 used for the experiment, and another equipment, the M4100, is the equipment of the island top of rack. So in the equipment of the backbone, you have a VLAN G for the data plan, another VLAN G for control plane, and receive another VLAN G for the other point. So you have a topology. I show a more detailed topology. Yeah, this is the physical topology above, and you have a lot of the static VLANs that creates the logical topology. In this case, when the experimenter go into the web interface and open all the aggregate menus, can define your topology based in this connectivity, and automatically the control framework creates the topology for us, for the experimenter. And in terms of the international connectivity, you have 2 links, one from the University of Bristol until São Paulo, and another from Ituquets in Spain until São Paulo. And one link is through Atlantic Wave and Internet 2, and another link to Rede Clara. In this link, you are using Q and Q. So when you receive the control plane and data plane from another domain in Europe, these 2 planes is going through the Q and Q. And when it comes to São Paulo, you open this Q and Q and separate. The control plane going to the VPLS cloud, and the data planes stitching with the data plane in Brazil. I have some problem. until now because it's difficult to establish the Q&Q security, has some problem. And the technical is working this week. And so because the link is set up, but don't work the Q&Q. And I hope that you finish this problem. And we're starting to connect with the ETUCAT in University of Bristol and UTH. And can create experimental among these islands. That's the idea. So, an overall view of the SDN research, we have 10 islands in Brazil, plus 3 islands in Europe. Control plane use VPLS, level 3, and data plane use VLANs with Q&Q. And for international connection, we have 2 VLANs. Yes, in São Paulo, separate control plane and data planes, map control plane to VPLS cloud, stitching, and enable layer 2 data flows in SDN. It's the idea. In terms of federation, Fiber was born in federation because it's a project that we have to connect university in Brazil, Europe, and you decide to use MySlice. MySlice is a web interface, a portal that's SFA based. So through this portal, the user can see all the aggregate managers in all islands and can select all the aggregation you use, and MySlice make the reservation in the. It's similar to FLAC. It's some tool like FLAC. In terms of authentication, we use CAFE, is a SHIB Federation Brazil, or LDAP. And so you have a LDAP based. In terms of authorization, you are defining the access rules. It's not finished. But the idea has a PI that authorizes all the users and create account, authorize create a slice, something. Operation, the NOC will be in Brazil. In the portal of the federation will be in Brazil also. You are monitoring all aggregation management and components of federation, not yet in production, not open to play, just for inside of the group. But the plan for October 2014, open for all the interesting to use the test beds. Just all. Thank you. One question?
I know the FIU location of GENI, Florida International, has been talking a long time about supporting SDN to Brazil and I assume to your testbed as well.
Yeah.
I was wondering, do you have anything unique that happens because you have all these wireless nodes connected to an SDN testbed? Do you see interesting opportunities for SDN in that environment? Because not all testbeds have that.
Yeah, I didn't understand the question. Because you have wireless.
You have wireless nodes.
Yes, yes.
And SDN.
Yeah, yes.
And you combine them.
Yeah, yes.
What do you get out of doing that?
Yeah, because when you start the project, you decided to create a heterogeneous environment, but you have one controller for the both resource. And the MySlice, when you use MySlice, you can preserve resource in the wireless testbed, in the SDN testbed, and connect all. I think that's maybe it should be an opportunity to create a new experience. I don't know how use if it's very helpful, but it's an idea to have all the resources together.
Yeah, we're just doing the same thing with the WiMAX in GENI too, and the
Yeah,
LTE.
yeah,
so
yeah.
It'll be interesting.
Yeah,
That's
because
an unusual kind of peering or
Yes.
exchange.
Okay.
Okay, if there are no more questions, do we have any last wise thoughts from Russ, who has now appeared? I'm not surprised. My brains would be dripping out my ears if I was you by now. Okay, well, thank you very much, Ayara. Can we have a round of applause for our great panel? And you're free to sit down now in the, oh, sorry. I thought you had something you wanted to say.
No, no.
Oh.
No, I wanted to escape.